Hey guys, so today we're going to be talking about reaction rates and things that can affect the rate of a reaction. Okay, so let's go. So what are some things that can affect how fast a reaction goes? A lot of these we've already discussed back when we talked about different types of reactions, and honestly, some of them are logical. So the first one is the nature of the reactants themselves. Reactions are, remember, the breaking of existing bonds and the creating of new bonds. Breaking more bonds requires more particles, and it requires the particles have more energy when they collide. So if you just need to break one bond, those particles only need to collide with a certain amount of energy. If we're breaking more bonds, then more energy needs to be supplied to that system. Because I'm hoping that you remember our old acronym, our old friend BARF. BARF stood for breaking absorbed, released when formed. So when we want to break a bond, we need to supply energy. And if we want to break more bonds, we have to supply more energy. So covalently bonded substances tend to be slower to react because they also tend to have more bonds than ionic substances. So ionic things will tend to react faster. Covalent things will tend to react more slowly. So our general order for that, from fast to slow, is ionic solutions will generally react the fastest, followed by ionic solids, and covalent substances will be on the slower end. Another thing that easily affects the rate of a reaction or how fast a reaction will go is the concentration. Now, what do I mean by that? I mean both the concentration of the reactants and the concentration of the products. Imagine this. You're in a room with 2 or 3 kindergartners. You know, I love this example. And you put a cupcake in the front of the room and you scream, "Free cupcakes!" and they all come running. Well, chances are they're not going to really bump into each other. There are only 2 or 3 of them in the room. But let's put 50 kindergartners in that room and put a tray of free cupcakes in the front, and you shout "free cupcakes," what's going to happen? Okay, you know that the more particles we have in an area, the more likely they are to collide. It's the difference between parking in an empty parking lot and parking in a parking lot where everybody's double parked and there's just one tiny little space in a corner for you to get into. Which one of those is more easy to park in? So if we increase the concentration of the reactants, it will result in an increase in the frequency of collisions. Therefore, the rate of the reactions will increase, and the time it takes for that reaction to happen will decrease because we're making it happen faster. We're increasing the rate. So it's faster if concentration or molarity of a solution is increased. So a 1 molar solution would be slower than a 2 molar solution, and that would be slower than a 3 molar solution, and so on. But when we're applying this practically, there's always a balance between wanting a reaction to go fast and wanting to look at its concentration and wanting to keep a reaction safe. So one has to look at those two in concert. Now, pressure. Pressure relates to concentration, because let's imagine that container again. Let's think back to gas laws. If we have a container and it contains 1,000 particles, and when we squeeze that container down, we increase the pressure in that container, what does happen to the effective concentration within that container? Well, it's going to increase, but only in a gaseous system, because remember, we can't squeeze liquids and solids, okay? So changing the pressure in a system only affects the concentration of a closed gaseous system. Closed being an operative term here, because if it were open, the gases would just go everywhere. So increased pressure means we have increased concentration, means we have increased collisions, means we have an increased reaction rate. And that is only for gases. Remember, increasing the pressure will only affect gases. Okay? So the third thing that can affect our rate of reaction is temperature. And this should make sense too, knowing what we know about temperature at this point. Remember, temperature is the measurement of the average kinetic energy of a system's particles. So if this is true, then when we increase the temperature, those particles are going to have increased kinetic energy, which means we're going to have an increased frequency of reactions because they're moving faster. This increases also their force of collision. If you have two cars going 10 miles an hour and they bump into each other, maybe you're going to ding their bumper, but nobody's going to get hurt. If they're going 70 miles an hour, well, that's a totally different story. So if we increase our frequency and our force of collisions, we're going to increase our reaction rate. Because remember, collision theory says that particles need to collide with sufficient energy and in the correct orientation. So far, there's nothing we can do to control the orientation they hit at, so we just make sure they hit more often so they have a better chance of hitting in that correct orientation. So collisions have to have enough energy and be in the right orientation or position for a reaction to occur. The fourth thing that can affect the rate of reaction is surface area. The analogy I like to use for this is sugar. Let's say I go to my favorite coffee shop and I order, I don't know, a latte. Let's be fancy. And I ask for sugar. If I ask for sugar and they give me a sugar cube, it's going to take a lot longer for my drink to taste sweet. Why? Well, that cube has less surface area than sugar in a packet, which is already broken down into granules. So surface area definitely plays a part. The larger surface area, meaning the smaller the particles are, more chances for the particles to collide and the reaction will go faster. If we have a small surface area, like our cube of sugar, or like a lump of reactant, this is one of the reasons why back when we did the lab where we drove off water from our hydrate, I had you reduce the surface area of those crystals. I had you grind them up. And the reason for that was that allowed there to be increased surface area to drive our water out from. So if we have a small surface area, meaning it's one single large particle or just a few big lumps, there are less chances for particles to collide and the reaction proceeds more slowly. Let's put this in practical terms. Let's say you've got a terrible pounding headache and you want to get rid of it faster. We think, well, if I can increase the surface area of this aspirin, maybe I'll feel better quicker. How can you do that? Well, the best way to increase the surface area of an aspirin would be to crush it, or even better, dissolve it in water. That's one of the reasons why, if you go down south, everybody uses something called Goody's headache powder. And all it is aspirin, but it's in a powder form in a little packet. You tear it open, you put it in a glass of water, and you drink it. It tastes terrible. They add flavoring, but it doesn't help. But I will tell you, it does work faster because you don't have to wait for that to break down in your stomach, dissolve into single pieces so that it can react with your nervous system in such a way as to relieve your pain. So it makes sense. So let's arrange these in order from the smallest to the largest surface area. Let's imagine that I have iron and I want to react that iron with an acid. I have 3 forms of iron. I have them all in exactly the same amount. Their mass is exactly the same. I have some beads of iron, I have some iron powder, and I have a solid bar of iron. Please put those 3 forms in order from the one that is going to react the quickest to the one that is going to react, from the smallest to the largest surface area. So if you told me the smallest surface area would be the bar, followed by the bead, followed by the powder, you would be correct. Now, if we ordered those in speed of reaction, what would they be? So in terms of speed of reaction, the fastest one would be your powder, followed by your beads, and finally your bar. The 5th way that we can affect the rate of a reaction is a catalyst. We learned about catalysts when we were learning about potential energy diagrams. What do catalysts do? Well, they lower the activation energy of a system, and they do this by changing the pathway that the reaction takes. Imagine that you are putting together a puzzle, Or even better, you're putting together a car. And there are two parts you need to go together, but they're very delicate and you can't touch them. And you're just kind of pushing them around, trying to get them to fit together. But then let's say your friend hands you something called a jig, which is a tool that allows you to put those things into position so that when you move them together, they'll click perfectly. That's kind of what a catalyst does. It helps to position the reactants so that they have a better chance of colliding with less energy supplied. And thus it makes the rate of the reaction faster. Now remember, catalysts themselves are not changed or consumed in a reaction. They can be used over and over and over. So once again, catalysts change the reaction pathway, they lower the activation energy, and that makes our rate of reaction faster. So let's look at a couple of examples. On example 5, as the concentration of our reacting particles increases, what happens to the rate of our reaction? Explain why. So you should have said something like, as the concentration of reacting particles increases, the rate of our reaction also increases because there are more chances for effective collisions, or more chances for the particles to collide. In order to get a reaction, we have to have those particles collide, and they have to collide with proper orientation and with enough energy. Example 6. What kind of conditions in terms of concentration, temperature, and surface area would make a reaction proceed slower? So let's imagine we need to slow a dangerous reaction down. We still want it to happen, but we want it to happen as slowly as possible. What conditions would we want to put that reaction under, thinking about concentration, temperature, and surface area? Let's think about that. What kind of conditions in terms of concentration, temperature, and surface area will make a reaction proceed slower? So, for concentration, we would want that concentration to be small. We would want enough for it to react, but not enough to make it start to speed up. We would want the temperature to be low. That would keep the particle speed slow. And we would want the surface area to be small. We would want to use perhaps a chunk of solid material instead of pre-dissolving it, and that might make our reaction proceed more slowly. So that's it for rates of reaction, things that can affect the rate of reaction. We're going to be putting this into practice, playing around with it a little bit in our next lesson.